So question 5, which is related to the Doppler effects and the pulse echo. The diagram shows a line spectrum. As I mentioned, like different elements have a unique line spectrums. And for a particular element is shown, like different elements give a unique frequency or a wavelength. We call that as a line spectrum. And line spectrums are identity of the elements as well. A star containing an element is moving away from the Earth. So we are observing a star. So this is a star we are observing. And this star is moving away from us. So if this star is moving away from us, what will happen to the wavelength which we receive? The wavelength should increase and the frequency should decrease. This is a wavelength. So red is having the longest wavelength in terms of the visible spectrum, and violet is having the shortest wavelength. So this whole pattern, the pattern will not change. The whole pattern will shift towards the red. So what could be the right answer for this question? A, B, C, or D? Which of the following spectra could be obtained from a light from the star? Is it A, B, C, or D? No, the pattern will not change. The pattern remained the same, but it shifted towards the longer side. So correct answer for this one is D. Why not A? If you see, like here, the pattern will not change. The pattern remained the same. Only the whole pattern shifted towards the longer side as it is moving. It will shift towards right. But what is the problem with option A? They flip the position. That's why it's totally wrong. Why B is wrong? Because all of them have spread away. So it cannot be like if either it will shift towards red or violet, but it cannot move one side move towards red and one move towards violet. It means like it cannot happen. Either it is moving towards or away. For this one, the pattern does not change and it is shifted more towards the violet. And for D, it has shifted more towards the red. The position, this position has changed. So the whole pattern is shifted towards the red. Here, whole pattern is shifted. This will happen if it was moving towards a blue shift. And this is happening when it is moving away. Is it clear? So if you compare the first line here, it has shifted towards the red. Any doubt in this? So the whole pattern has shifted towards the red, means it's a red shift. The velocity of the longitudinal wave in the spring is also determined by finding the time for a pulse to travel along the length of a spring. The spring is filled while the pulse is created at the bottom and allow the reflection from the top. The pulse travel back up and then return. And this is show that the velocity of a longitudinal wave in a spring determined by this method is about 5 meters per second. The time is there and the length of the spring is also given. And this is actually 42 times. It goes like example, the spring is there and we produce a wave in a spring. It send and return back how many times? 42 times. the pulse travel up and back down the spring 42 times, so that the velocity of a longitudinal wave by this method is about 5 meter per second. So we have the distance. So speed is distance divided by time. It can be done different ways. We can use a distance. The No, it can be done two ways. One is by using the pulse length, it can be done. Another one is by using I can use a pulse length if I know the length of the pulse and I know the time of the pulse, like the time interval for one pulse. So we can use a formula, speed is distance over time, and I can determine the speed. The second one, so it goes and come back, and this is 72 centimeter. And 42 pulses are there. So just use the formula, speed is distance over time. So what is the time for one pulse? If we do 0.72, yeah, it will be the same thing. Like example, 0.72 centimeter is there. That is the distance multiplied by 42, because 42 times, and the total time is 6.17, because it's like you use a formula that speed is distance divided by time. So the length of a spring is 0.72 and like 72 centimeter 0.72. So it is going 42 times. So in 42 times, how much is the distance covered? So 0.72 into 42, that is a distance total cover. And 6.17 is a total time. So when we divide them, we'll get the speed that is 4.9 meter per second. That is one way of doing the question. Another way of doing the question is like you find the time for each pulse, like 42 times it is going for 6.17 seconds. So for one, it will be x. Just cross multiply. So x will be 6.17 divided by 42. So that will give us the time for one pulse. And then the distance divided by time, you will get the speed. Is it clear, this one? So it's the same method, the total distance 0.72 times, because it is going 42 times, and the total time interval. This is a total time, okay? That's why I did not multiply this. The time it takes, that is 6.17. Is it clear, this question? Any doubt in this? 42, actually, this part is, was 42. In the question, it's just editing mistake. It is 42 times. Question 7. Ultrasound is used to investigate the blood in the artery in a human body by detecting a Doppler shift. This Doppler shift is used to measure what? What we can use, where we can use this? A Doppler shift. diameter of the artery, a Doppler shift. The Doppler shift can be used to determine the relative speed or the frequency, not the size. That a pulse echo is for the size. So when we compare the diameter of the arteries, no, diameter of the artery, if we want to determine the diameter of the artery, we'll use a pulse echo. Like we send the signal and it will bounce back. Size of the particle in the blood, the size of the particle in the blood, no, the Doppler, because Doppler effect can be used to determine the speed at which the observer or the source are moving, or the frequency, apparent change in the frequency. That's the Doppler effect. Not the size of the blood particles in the blood or the temperature. It is used the speed at which the blood is moving. We can determine that by using a Doppler effect. Question 8. When a light from a distant star reaches us on Earth, its wavelength appear to be shifted towards the red end of the spectrum. This is because why? Question 8. So if the spectrum, it is towards the red end of the spectrum, you have violet, indigo, blue, green, yellow, orange, and red. So what is given? The distance traveled by each successive wave has increased. So what? Yeah, the distance because of the Doppler effect, as it is moving away, the source is moving away. So what will happen? The distance traveled by the each wave, successive wave has increased. That's right. The frequency of the emitted has decreased. No, the frequency of emitted will never change. The speed of the star has increased. The speed of the star increase or decrease depends on the change in the frequency or the wavelength, but it does not give an idea. Like here, you don't have like speed of star. Maybe it if the speed of the star was increasing, then what will happen? There will be the frequency which we receive continuously. It will change. Or if the speed of the star was changing, this frequency we receive continuously it will change. But here in the question, they did not mention that the star is accelerating. That's why we cannot select this. The star is emitting a longer wavelength. That's also wrong. It does not emit. Star is emitting the same wavelength, but what we receive on the Earth will be longer. Is it clear? So remember, the frequency which is emitted will not change. It's the received one will change. In question 9, the early experiment to measure the speed of a light involved the timing pulse of a light between the reflecting back from a distance mirror. If the pulse of a light was emitted and detected 0.24 millisecond, what is the distance between the mirrors? So we send the pulse, and we receive it back. We have the formula because we need the distance between the mirrors. So it will be 2d divided by t. So d will be v into t divided by 2. V is the speed of a light, which is 3 into 10 to the power 8. T is the time. This T is the total time for the pulse to send and receive, which is 0.24 milli, means 10 power minus 3, and divided by 2. So what's the answer for this? So 3.6 exponent 4. So D will be the right answer. In question 10, a stationary observer hears a sound emitted by a moving source. So there's a stationary observer and the source is moving. It might be moving towards or away. They did not mention that. This produced a Doppler's effect, which is, what is the Doppler effect? C and D are totally wrong because the speed of a wave does not change. So either A can be an answer or B can be an answer. Then the change in the frequency of a sound emitted from the source. Again, that will not change. The source frequency never changes. The observer is changed. So change in frequency of a sound heard by the observer is why A is wrong because source frequency never changes. The source frequency like remain 100. But what is observed is has changed depending on the relative motion of the source and observer. Source frequency never changes. Even it is moving towards or away. In question 11, the last one for a discussion, ultrasound scanning can be used by doctors to obtain information about the internal structure of a human body without need of for a surgery. Pulses of ultrasound are sent into a body from a transmitter placed on the skin. The ultrasound has a frequency of 4.5 megahertz. Suggests why a wave of high frequencies are called ultrasound. Actually, this is related to, yeah, this is one thing, but why we call them as ultrasound? Because it is beyond the audible range. Audible range is 20,000. So it has a frequency more than 20,000. That's why we call them as ultrasound. So ultrasounds are actually, why we call them as ultrasound? Because sound waves which are having a frequency more than 20,000 hertz, we call them as ultrasound. A pulse of ultrasound enters the body and it is reflected, returned to the transmitter 1.6 exponent minus 4 seconds. Calculate how far the reflecting surface is below the skin. And the speed of the ultrasound in the body is 1500. So we need the distance here. The reflection is given. So we can use the formula speed is distance divided by time. So this will be 2D because it goes and come back. And the total time is there is 1.6. So this T. So if I need distance, speed multiplied by time divided by 2. So 1500 times 1.6 exponent minus 4 divided by 2. So we got the distance which is 0.12 meters. So 0.12 meter is a distance between the skin and the organ. State why ultrasound is transmitted in pulses. Like why not a continuous signal? So that we can, the idea is that we can send one pulse must return back before the next is sent. Otherwise, we cannot be able to distinguish between the one which is sent and received. So this was about the Doppler effect and the pulse echo. Tomorrow we will do diffraction and the standing waves.